here. So do we have any new members? Or relatively new members? Some new faces I haven't seen in a while. So I'll just give you a little debrief on the gathering of the guilds. It was last weekend. We had the club here had a 30-foot booth, and there were seven of us there selling, and then two other members, John Beechwood and Kevin, had their own booth selling it. There was the Pacific Northwest Turners Guild, and we had another big turner, John Harden. So we probably had 100 feet of wood turning sellers there. There was a lot of competition. Our booth, we did, let me think, we did, what did I say, $6,500 or $7,500 between almost $1,000 a person. So the Northwest Wood Turners did that. The Guild of Oregon Woodworkers, they did about $6,500. So it was a good show. Unfortunately, after 2 months of rain and crappy weather, the two nicest days we've had in about 6 months happened to be on the weekend that we had the show. But we still had about 10% more than we did last year. So the attendance was close to 14,000 people that came through the 3 days. So it was a pretty successful show, I think. And so we'll get ready to plan for next year. What else? We have, if you've been reading the newsletter, we have two wood czars now. Mark excuse me. Mark McNamara is doing the west side, and he has one this next Saturday in Cedar Mill area. And Pierce is going to do Vancouver and the east side. So what we're doing there is that we're going to start supplying wood for the members here at a very good price. If you come to open shop or mostly open shop, you'll be able to buy some really good pieces of wood at very aggressive prices. What else do we have? Should we do show and tell? Who's going to be our show and tell czar today? Hey, by the way, we have some $10 certificates from Craft Supplies, and we're going to be giving those out for show and tell. And we need a show and tell. Who wants to do show and tell, guys? Steve, you don't look like you're doing anything.
You've been voluntold.
Okay. So John Beechwood?
Yeah.
You want to talk about your dinosaur egg?
That's it.
Shake it.
That's a maple burl that I colored the top of, and then I cast deep pour epoxy around it and then turned it. I used an airbrush and painted it with a dye, and then I sprinkled glitter on it.
Nice.
And I had to sand it to about 20,000 grit to get it to polish. And I used the diatomaceous earth, which worked really well. And then I used regular buffing compound like you would for your car to get it to come back clear. But it sat for 5 days in a pressure tank.
How do you do the diatomaceous earth?
You just put it on a paper towel or
With a little wax.
with a little bit of water and spin it. And the more you spin it, the more it breaks down. So it gets finer and finer and finer and finer and finer.
Very cool.
And eventually all the scratches that go out of it.
So having the stand be the same piece of wood decreases the likelihood it's going to fall off the table, et cetera.
Correct. It's not going to fall.
Right, nice.
deceiving though, when you go to try to pick the egg up. and
It
the
is.
egg Comes with it.
We have a couple of mirrors here from Don Jensen.
It was my first time batching. I did groups of 6 for the gathering of the guild, and it was a great learning experience.
On,
The mic so Zoom can hear. Who can't hear?
Zoom.
Oh, Zoom. Oh, sorry.
Yeah, I batched, I made 13 of them, batched 6 and then 7. It was a great process for getting my tool control improved and my finishing techniques. So it was a good, fun project.
we'll go with Kevin.
This is the second piece I've turned out of a batch of really curly firewood that I got from Steve Walgrave back in February. And I brought a chunk to the raffle that month, so somebody ended up with it. If you haven't turned it yet, this is what it'll look like, so. Tried and true Danish oil.
Excellent as usual. Don't go away. You want to talk about your pieces?
Okay, these are practice tremblers, different woods. I'm playing with different woods on it. So the one is oak, holly, on the either ends, some black walnut, boxwood, jatoba, and cherry. I've learned that you cannot do this kind of work with mahogany. It's the fines, the really skinny pieces. There's just no strength there, and it's an exercise in bad words.
Where'd you find the boxwood?
I got that when I was in France. The man I took the class from, he had some. So he actually has it growing on some of his property, the lucky SOB.
What tool are you using on the thin section?
I'm using a Badan, a small Badan, and then I'm also using I'm using a parting tool for the fine one, and then I have a hacksaw blade that I cut into a very small parting tool also for some of the finer stuff. It's interesting. It's
Fantastic.
Thank you. I'm long way to go.
Thank you. We have some salt and pepper mills from Jim. Is it Diamond?
They're all made out of plywood. I don't do a lot with plywood, but I thought it'd be fun to try some things. The one in the middle, the colorful one, is the piece that I got at the symposium. The other two I laminated up myself and dyed them, and the finish is wipe on poly. I don't like wipe on poly, but I put it on something like this because it wears well. The only thing that I learned about the plywood is when you glue it up, when you turn it after gluing it up, if the plies run in the finished piece vertically, it's fairly easy. If they run horizontally, like the one all the way on my right, the green one, you have to be real careful in rounding them because the plies actually separate, and it's not the glue joints that I had, it's plies themselves will separate. So you have to be kind of careful in rounding it, and after you get them round, they're like anything else. Just something I got at Woodcraft. Baltic birch, I think it is. Yeah, it doesn't have any voids or anything in it. No.
That's got too many holes in it.
No. No, it actually has very few voids in it.
Thank you, Jim.
Sure.
Right. So these are turned teapots. The body is one piece. It's a preview of my July demonstration. Both of these are maple. This is a spalted maple. This is a figured maple. And this is the chuck I'll be demonstrating. It's a off-center donut chuck.
And you turn a sphere with a cone on either end, and then you have to put it in here off center and tilted to have the other cone on center so you can drill and turn the spout. And that means you have to elevate the piece off of the base plate with a little pedestal there. So more to follow in July.
Okay, I guess we're ready for Mike. Yeah. So thank you everyone for sending your questions in on the poll. I think we had about 15 submissions. And Mike looked at all of them, collated it, and put together this presentation, which we will also put on the website or on the our YouTube channel when we're done here. So Mike, put you on.
Hello, can you hear me? I imagine you all can hear me, so that's not really a problem. All right, I want to talk tonight a little bit about wood finishing, a subject I've thought some about the last several years. Getting this talk ready, I remembered why I had never done one like this on this topic before, because it's impossible. You just can't do it. There's too much to talk about, too many different things. This needs to be about 3 different demonstrations with the 3 different branches of the finishing materials. Well, what I want to do tonight is looking at the questions that we had. They were generally about finishing processes, not necessarily specific finishing products. So we're going to talk about the sort of general lay of the land with finishing products. We're going to define a few terms that get used, but most people don't know what they are. And then we will go from there. So tonight, we're going to talk about wood finishing in a grossly oversimplified manner. You know, you measure your audience, and this looks like a simple group, so we'll just keep it on the down flow for everybody. Now, every talk that I give and every talk that I go to, I expect to hear the following line: "This is just one opinion. This is the way I do it. This is the way that I see things, but there are, you know, a dozen different approaches to every problem." So this is just one opinion. Although I do know something about the chemistry of the finishes. And as it turns out, the area of chemistry that I worked in for 40 years actually falls down fairly closely to the chemistry of the finishes that I use. And actually all of them are very similar in their chemical makeup. They're completely divergent in their sources, but they wind up relying on one set of reactions that are the essence of polymer chemistry. So we will talk about the different kinds of finishes. I have a couple of movies in here where it's just easier to show you than to explain it. And these are movies that are on my website, the doctorswoodshop.com. The finishing process, you know, finishing wood is as I say, very much like choosing wine. There's only one important question: what do you like? What do you want it to wind up being? And there's a divergence in that metric that is just all over the place. Now, this is true for the flat work. It's true for turned projects also. Because you can apply a finish, you can do different finishing techniques. You can finish your piece any way you want to. But one thing that I do want you to get right now is that you start the finishing process of your piece when you pick up a tool and you touch it to a piece of wood on the lathe. Everything that you do from that point forward affects the way your product is going to turn out as a finished product. And I refer to that a couple of times as we go through the evening. You can break down what do you like into a number of different categories. And there's just, 5 that I thought of. Surface texture, the actual surface augmentation is in fact a finishing process. How do you want the surface to feel? Do you want it to be colored? So staining, bleaching, dyeing, including colored materials. If you're doing casting work, including various colors in your casting materials. These all get to the question of, what do you like? Reflective index. Do you like a satin finish? Do you like a gloss finish? Do you like a flat finish? Do you like a matte? Do you like a semi-gloss? It goes on and on. But what do you want that reflective index to do on your piece? And we're going to, if at the end you want to learn more about waxes, there's a discussion of why pieces are shiny and what we're doing to change that refraction of light from the surface. The surface augmentation we've talked about, that goes into texture, the piercing, the roughing, the carving, those little repetitive chips that Caro takes out of his bowls. That's a finishing technique. And I'm going to leave that one to Bill to talk about one final day. And then finally, what are you going to do with it? What's the final purpose of this piece? Is it, a gorgeous hollow form that's going to sit on the piano and look beautiful? Is it a salad bowl? Is it a spoon? Is it a pepper mill? Is it an ice cream scoop handle? What's it going to be used for? That comes into an evaluation of a decision of what you're going to do, how you're going to finish that piece of wood. Finally, what kind of wood is it? I didn't put that in there, but I should have. Different woods take to different finishes in better ways. There are woods that are very close grained. We think of the exotics, the rosewoods, Paduke, ironwood, bloodwood, all of these very fine grained woods that you're going to finish very differently because the nature of the wood is different. It's going to take up and hold and use the finish differently than, say, walnut, a broad grained wood, or oak, or ash, or any wood that has a very broad grain structure. Speaking of which, I guess I can't go very long without thinking about a new product. I started playing with some combinations that will be specifically for the open grain woods, as far as one-step finishes, things sort of like Pens Plus, but with additions to deal with the wider grain, so that it makes that grain look a little better. It penetrates a little bit deeper. So the different woods, knowing the wood that you're going to use, unless you spend your turning life with maple and cherry, and there's not a thing wrong with that, there will be some variations in what you need your finishes to do. So what are we going to do tonight? Well, we're going to outline and define some terms that we use, but we really don't know most people don't know what they are. And if you can clarify what you're talking about, it makes talking about it a little easier. That's a point of view not widely shared these days in the political scene, but we'll try to do a little bit better. So we'll start with some terms, and I hope after we get some of these terms laid out, some of the finishes that you have used in the past will become a little more transparent as to why they do what they do. We're going to talk about some of the most common choices for finishes. This is when I realized this is an impossible task, because there are, well, you go back to what do you like? And then under that, there are a dozen variations where you can get to what you want. And you need to know a little bit about the finishes that you can use. You need to know about the wood that you're going to be using it on. And you need to know something about techniques. So the most common choices for finishing. Now, it's just the You know, when someone invites me to give a talk, they get the baggage that comes with me. And that baggage that comes with me is viewing the world through the light of chemistry. You know, the saying has always been, if you understand the chemistry, the biology will make sense. If you understand the chemistry, the function of the end chemicals will make sense. And the way they behave kind of makes sense. And we'll talk about polyurethanes. There are a dozen different polyurethanes, but you can look at the ingredients in those polyurethanes, and the properties of that finish start to make a little bit more sense than if you just sort of take them at label value. And we're going to take a look at the questions, some of the questions that were submitted by the members. I got Rogers first because he asked all of the questions right off the top, so we can just answer them all at one time. But there are a few others that you will see along the way that fit with the topics that I'm talking about. So what are we not going to do? We're not going to examine surface augmentation as a finishing strategy. I'm going to leave that to Caro and anyone else who wants to talk about it. It's fascinating and deserves a talk of its own, certainly to try to get across the methods that are used. We're not going to discuss stains and dyes. When it comes down to what do you like, stained wood is not one of the things that I like, so I don't think about it very much. The dyes, however, as part of the dyeing of synthetic materials, you guys get me again next month. We're going to talk about alumalite and the production of hybrid materials, and the use of dyes there is integral to the process and actually one of the most fun things about it. But if it's real wood, we're not going to dye it, we're not going to stain it, and we're not going to discuss bleaching, which is a topic I'm just now beginning to appreciate, the things you can do with bleaching. You know, and again, I'll leave that to Caro to discuss. That's done with very strong bases, and I did 40 years in the chemistry lab, and I got away without a major bleach burn. So I'm thinking I'm just not going to press my luck on that one any longer. Now the most general consideration of a finishing material is something that we refer to as a top coat, a film finish, polyurethane, shellac, any of the other polyurethane finishes, anything you put that stays on top of the wood would be a film finish. We have to consider what's in that film finish and how is it reacting with the wood and with itself. The other thing I want to get across to you tonight is that, as I said before, you start finishing your project the first time you put a tool to that piece of wood. And no finish is any better than the surface to which it is applied. You can't expect to make the silk purse out of the sow's ear. If you've turned crap, it's going to finish like crap. So let's get that even with yourself now. There are going to be projects that do not turn out. Go back, do them again, and don't try to salvage the project in the finishing process. The finish, I see finishing as sort of the first decimal place. You know, you've done 99% of the project. Your finish is going to finish off that last tenth of the appeal of the process. The wood will speak for itself. What you've done with the wood as far as shape and milling of the wood, molding of the wood, the finish will just sort of dot the I's, cross the T's, and finish. So the surface, how do you improve the surface? This is sort of a list of things we will see in a couple of different places. First, on improving your finishes, make better cuts. If you're not getting good, even cuts across the wood, you're not going to get a readily, easily finished piece of wood out the other end of the process. Sharper tools. Somehow I always wind up coming back to sharpening, but you can't overestimate the importance of a sharp tool to the end project, to the end look of the project. You're going to get smoother, more sweeping cuts. You're gonna have less tear out to deal with. And then you're gonna wind up with something that your finish can add the last 1% to get a truly nice and worthwhile project. And then finally, sanding. And we sort of overlook sanding as, you know, it's not a mortal sin to rely on sanding to clean up your surface. It's not even a venal sin, but we sand and try to get through things very quickly. Sanding can take time because you have to sand with thought. You're not just rubbing broken glass across this. Well, you are just rubbing broken glass across the surface of the wood, but we try to do it with a little more tact than that. The things that I have learned through the years is that we don't sand really long enough. We tend to go quicker through the grits than we should. If you can still see grit marks from the last grit, you're not ready to move on. A grit should be capable of taking out all of the grit marks that you started with. Now you leave new smaller ones, but if your grit marks are not getting smaller as you're going through, you're not sanding effectively. And I've found that one of the things that I recommend is use of a sanding lubricant. I used to recommend, say, lubricating your sanding from the first sandpaper on up. I've cut back on that. I've ruined so many, turning jackets with the oil, up and down, that I now limit the lubricated sanding to the last 3 grits or so. If I'm going to 600, I'll start up at 320, 320, 400, 600. We'll get a sanding lubricant. Sanding lubricants, walnut oil works fine because I've always got it right there. That's about the only thing mineral oil is good for. Mineral oil as a wood finish, I will malign it again later, is not worth a damn. It evaporates, it supports bacterial growth in the wood, but it lubricates very well. It lubricates as well as the walnut oil, and it's not going to make a mess on your coat. It'll stain, you'll get a dark oil stain, but it's not going to get colored. So keeping mineral oil to lubricate your sanding is a perfectly good and less expensive, to be honest about it. Mineral oil is considerably cheaper than walnut oil or any of the other lubricating oils, and it works just as well. The sanding lubricant, I didn't grab the sanding lubricant movie to put in here. It's on the website, as I said, under on the page that says videos. A sanding lubricant traps the sawdust, and so that you are now sanding with a cutting tool, your sandpaper, but you're also polishing with a buffing compound the sawdust in a colloidal suspension with the oil, whatever the oil is. So you're sanding and polishing at the same time. You're going to get a better finish in a shorter time. That's going to give you the time you need to go through all those intermediate grits to get where you need to go. And you'll get to somewhere, and I think I go through this again, and I recommend that you sand 1 grit further than you think you need to, just to sort of dot the I. With the sanding lubricant, you'll get more out of that extra effort that you put into sanding than without it. So the people ask how far do you sand with the common woods, things that we wouldn't consider exotic, 600 grit, 400 to 600. If it's a particularly, and again, that's going to vary with the wood. If you've got a piece of walnut that is from a very old tree that has very close growth rings, where you've got now a tighter grain than you would have in your typical walnut, your average walnut, the walnut that grew in the walnut plantation out there where it's watered and it grows very fast. If you've got that tight grain walnut, that'll take 800 and even 1,000 to actually get the best sheen on that. The Cocobolo boxwood, one of my favorite woods, but it's just damn impossible to find. I was showing him a picture of a chateau in France that I visited that had the French boxwoods all over the ground. And in the kitchen, they had this basket of boxwood cut up for firewood. And I'm thinking, no, this is wrong. Can I steal it? Can I get it on the airplane and get it out of here? And my wife prevailed on me and said, no, this is really not a good idea. They will notice. But boxwood, if you ever have a chance to turn a piece of boxwood, it's really just a joy. Very tight grain, up to 2000 grit. Now, keep in mind, if you, the non-sandpaper sanding materials, things like micromesh, they're going to talk about grits and micromesh up to 20,000. Those are not standard sandpaper grits. The 20,000 micromesh is equivalent to about a 6,000 grit P-scale sandpaper, but it's still a nice fine sandpaper. So using sanding to get the look on the wood the way it should be, and that is without any scratch marks. And you know how you tell scratch marks, right? You go and you find a flashlight that's got a daylight blue bulb in it, and you shine that on the wood. Because our eyes are most sensitive to the frequency of the blue light, if there is any sort of scratch on that, that blue in the bulb will show it up and you'll see it. And you get to throw it down and pick up your sandpaper again and kind of start over. But sand until you're satisfied that you have given that piece of wood the degree of finishing that it deserves. Cocobolo is going to make you look good. Take good care of the cocobolo before you finish your project. Why do we finish wood? There are lots of reasons. Remember, wood is the bundle of straws, and I actually made a bundle I'm going to bring out to the class on Saturday, so we will have a bundle of straws to look at. So the side grain and the end grain, you're looking at two reflective surfaces. In a bowl, it becomes a more important thing. The finish is going to sort of de-emphasize the look of the side grain and the end grain. So it sort of blends the wood together, but we're using a finish to actually close the grain of the woods. Once you turn a piece of wood, once you get the bark off of it and the cambium layers and it dries out, those straws have spaces that will start to take up air from the room. With that air comes oil, and eventually you're going to see there's a patina of oil on the surface of your wood. Your film finish is going to keep that out of the wood. It's going to prevent discoloration of the wood later on. And it keeps the dust out of the wood. It preserves it. So it will close the grain of the wood, and it stabilizes and protects the surface of the wood so that fingerprints don't show up quite so bad on the wood. You get a little bit of protection against dropping. Things wind up on the floor now and then, and sometimes a hard finish will in fact protect that against some of the physical destruction of the grain. And a finish, if properly chosen and properly applied, can add accent to the grain and figure of the wood. The best example of that is what flat workers call French polish, what I call a high build friction polish. It's the simplest of finishes. This is the finish that Bob Tuck taught us how to make in the first class all of us took from him years ago. You know, it's the oil, shellac, and alcohol. And in the flat work, the French polish, apply it with a cotton puff wrapped in cheesecloth, and you pick it up and you literally slap the wood, and that collision with the wood heats the surface. It's as close as you get to friction polishing in flat work. And that French polish, if you've been to the palace at Versailles, they have a collection of period tiger maple that is as wood goes, it just jumps at you. It calls you from across the room to come look at it. And that's finished with French polish. Now, when you're going to have an army of servants, you can French polish your furniture to maintain it, because it will pick up, particularly with the quality of shellac and oil they were using, it's going to pick up all of the lamb fat from the kitchen that's wafting up the stairs, and it has to be refinished about every 6 months. But that clear grain accents, or that clear finish accents the grain of the tiger maple, brings up the color. And this is why I say, people say, well, what should I finish a hollow form with? I say, well, you can finish it with whatever you like. Those occasions where I have something that I want people to see the grain, I use the high build friction polish because you can just keep adding layers of finish to that. There's no limit. And the more you add, the more it brings the grain out until, you know, you've got 2 inches of finish and 1 inch of wood. And then you probably ought to stop then. But, you know, that sort of a choice of finish will bring up what your wood has to say. And these are things that you need to think about before you charge off into your finish. Now, can we separate the finishing elements, finishing agents into big groups? And the answer is yes, we can. We can talk about non-penetrating finishes and we can talk about penetrating finishes. They're sort of self-explanatory. A non-penetrating finish would be like a wax. It's not going to go into the wood, although if you heat the wax with friction polishing, you can force some of it into the wood. The wax does not get drawn into wood the way that other finishes do. The chemistry of the cellulose and the chemistry of the wax are sort of diametrically opposed. But we can think of, for this case, we can think of wax as a non-penetrating finish. It's going to sit on top of the wood and it's going to close the grain. It's going to cover up bumps in the surface of the wood. And we're going to talk, as we go along, we're going to talk about refractive index and reflection, shine. The basis of shine is reflection of light. Now, light comes in, and ideally, we want that light to strike our wood surface, turn around and go back out by exactly the same path that it came in. That way you have no refraction. You would get the maximum reflection off the surface of the wood, and it's going to shine like a mirror. That doesn't happen very often. Even if you've done a really good job with your sanding and your sharp tools and your clean cuts, wood is going to have variations in it. You know, if we think about the scale of a photon coming into a piece of wood, you know, it's hitting that piece of wood that even if it's really good, it's going to look like the Himalayas. You know, it's up, it's down in the physics scale of a light particle. Our job is to fill in the canyons. We need to close up those canyons between the mountains as best we can. And that's part of the job of the finish. We sand off the top of the peaks, but we use something to fill up the valleys to get a little better, a little truer reflection of the light off the surface of the wood. So the non-penetrating finishes, wax, epoxies. Some people just use an epoxy glue as a finish. It doesn't go into the wood. Very tough. The acrylic, they're referred to as resins, and technically they are, but we're going to talk about what resins actually are in a minute. And we can have a discussion about whether epoxy resins are actually resins. But whatever it is, the acrylic is not going to go into the wood. It's going to stand on the top and it's going to reflect very clearly. These are very hard finishes where your protection, the aspect of protection is more important than maybe what it would do for the surface of the wood. The penetrating finishes, on the other side of things, are the things that are going to go into the wood. And by going into the wood, they affect the way the wood responds to light. They affect the way the wood responds to touch, and so forth. And within the penetrating finishes, we actually have 3 subcategories that we'll touch on as we go along. One is an evaporative, and that would be a finish that the solvent evaporates and leaves behind the material that is actually going to be the finish. Shellac is the one that first comes to mind there. Okay. Then we have a reactive finish, which means that something has taken place within the finishing material itself. A chemical reaction has taken place, and that is what's actually sealing the wood. And then finally, a coalescing finish, which is wax is sort of a coalescing finish. And if we talk about wax, you can see that a little later on. But what that means is that it's just sort of sticking together. There's no change there's no phase change and no state change. We talk about drying. And you take a water and you put a drop of water on the table, and eventually that water is going to disappear. And we say that water has dried. It has gone from wet to dry. The water is evaporated and is in the air now. When we use the term drying, with regard to finishing materials, we're talking about something that's very different. For example, paint. You take take latex paint and you paint it on a surface and it's a liquid. And then a little bit later, it's not, it's a solid. What's happened to it? We think, well, it's a latex paint, so it's a water base. So the water is evaporated and now this has become a solid. No. Latex paint really doesn't have any water in it. What you can do is you can thin it with water to make it more tractable, but that water eventually gets soaked into the finished material itself. What's happened with the latex paint is there's been a change of state. We have something on the scale of a reactive drying or a coalescive drying. The latex molecules, which are basically naturally occurring fatty acids, remember the term, we're going to talk about fatty acids later. Those naturally occurring fatty acids have coalesced, reacted with each other and become a solid. The water is trapped in there. It didn't evaporate, it got used up. So when we talk about drying oils, we're talking about oils that are going from a liquid state. Walnut oil is a liquid when it comes out of the walnut. When it becomes a solid, after you put it onto the wood and friction polished it, nothing evaporated. It's all still there. What's happened is that the walnut oil molecules have reacted with themselves to become a solid. They've undergone polymerization, or in a broader context, plasticization. We're going to talk about plastics tonight, of all things, but really the chemistry is the same. You have long molecules that could be monomers in our situation. They react with each other and they become polymers. Polyurethane, polyacrylate. And the natural oils or the synthetic oils can react in the same way to go from the monomer, the fatty acid, the oil state, to a solid, the polymer state. So let's talk about what is a resin. Well, a resin is a word that we throw around a lot. We talk about acrylic resins, but really resins are supposed to be natural products. A resin would be something that's produced by a plant or some other natural occurrence that has polymers within, or has molecules within that secretion that are held in suspension by a liquid. Pitch pine, pine pitch is the one that comes to mind. You have the pine pitch solids and you have the liquid, which is going to go become something we know as turpentine. So if you take the pine pitch and you take some other pine pitch over here and you boil the turpentine out of it, you have a resin that you're going to dilute, which you can now apply to the surface of something, and you will get a coalescive polymerization, a hardening of the pine pitch on that surface. That's a little crude, but basically that's the nuts and bolts of it. So a resin is the polymer part of some material. We can think of actually walnut oil as an all-inclusive resin. It has both the liquids and the monomers that we're going to react and undergo a state change. So we have a resin. What's a varnish? We talk about varnishing things. Well, a varnish would be if we took our pine pitch and somebody else's turpentine and diluted our pine pitch with that turpentine so that now we have the pine pitch solids and we have more of a liquid. But we can now apply this with a brush or a rag, and that really is a varnish. A varnish is a resin that's been diluted with a solvent. And you can dilute that as much as you want. If you start diluting it to extremes, you get what we call a lacquer. A lacquer is a type of hard and usually very shiny resin finish that is the resin molecules have been diluted to a very great extent to where they can be applied to very, very thin layers. And this is where you have an evaporative finishing, because that solvent that's carrying the pine pitch or whatever resin molecules you're using, that will evaporate, and allow the pine pitch to harden by its own natural polymerization. So varnish and resin are the same thing, really diluted to a different degree. We very seldom use pine pitch as a finish. We do use varnishes as a finish very often. But keep in mind what's in that. That's a resin that you're using to actually seal the wood grain. And that can be any number of things. That can be pine pitch. That can be plastic. That can be polyurethane monomers that you're going to put onto a surface that's going to harden into a polyurethane layer. So a lacquer, we can think of as a very thin varnish. One of the questions was, what's the best way to apply a lacquer, brush or spray? Well, it's if you brush it on, you're going to have to get enough of it to apply a relatively thick coat of that lacquer onto the surface, and there's a very good chance it's going to run. Whereas if you spray it on, you're spraying on, by definition, a very thin coat, and you have a better chance of getting that to dry without distortions in the surface. Shellac, probably my favorite finish. We've been using shellac for 3,000 years, possibly even longer. Shellac is made from the secreted resin of the female lac insect, which grows on the trees of in India, Thailand, other places in Southeast Asia. And it's literally, if you've ever had a plant with aphids, you'll see the secretion of the aphids that the ants come up to eat. That's exactly like shellac. You'd have to have a lot of really aphid infested roses to try to harvest the shellac from your garden. But a comparison of materials, that's exactly what you've got. So they, about this time of year, they go out into the forest and they literally beat the leaves, and the shellac the plastic, the secretion falls off onto towels or rags underneath. They collect it. Takes about 100,000 lac insects to make a kilogram of shellac flakes. And so that's a lot of work gathering it. I wonder why the price of shellac keeps going up. And I think about where it comes from and how it gets harvested. And then I understand exactly. I would feel better if I knew that extra money was going to the people knocking the stuff off the trees as opposed to into Zinzer's pocket. But it is what it is. But anyway, the shellac, is shellac a varnish? That comes up. Well, I've described this as a resin, but a varnish is a reactive finish. In a varnish, you've got these monomers reacting with each other. Whereas in the shellac, what you've got is just an evaporation of material, leaving the shellac to form its own shell again. So that's an evaporative finish, not a reactive. So shellac and varnish, although they look remarkably the same in place, are not the same class of finishes. What about polyurethane? Polyurethane has always been sort of a mystery to me. The what do you like standard comes up again, and I don't like polyurethane. You know, on the company checks of Doctor's Wood Shop, it says wood should look like wood, and polyurethane looks like plastic to me. If you like it, go for it. It's a great finish. It's easy, it's durable, it'll last forever. If you know what you're looking for, you can fine tune your polyurethane to get a very good model of what you want, because as we'll see, the molecular structure of the polyurethane is very variable. Polyurethane was developed by the Bayer AG Corporation in 1937. There's Otto Bayer playing with his new toy. That first polyurethane was a diisocyanate. You notice when you see the big round rings, I think you should think about light absorption. Those aromatic groups absorb light, which is why the early polyurethanes turned yellow. They absorbed the light that drove the chemistry in a different direction. So you wound up with a yellow polyurethane. Now there are what are called aliphatic polyurethanes. That is that they're not aromatic rings, they're long chains. They don't absorb light and they don't turn yellow. But the difference between the ring and the chain is that the chain can bend. So the aliphatic polyurethanes have more flexibility. They're better on a surface like a floor that's going to be bent up and down. If you look at the safety sheets of the polyurethane, it'll tell you what sort of polyurethane it is. It'll say aliphatic or aromatic polyurethane. If you're looking for something you think is going to have to bend a little bit, the pepper mills, spoons actually are good uses for polyurethane if you want a shiny finish on your spoon, because the urethane, the aliphatic urethane, is not going to crack as the spoon bends. So even in polyurethane, there's an option to find exactly what you want for the type of job you have. The name urethane comes from I had a pointer somewhere. If you look on the other end of the aromatic ring, you'll see something that looks like urea. In fact, the chemistry of the polyurethanes, they got their name because they reacted very much like urea. Now, urea is the end product of protein metabolism in animals. It's an outstanding fertilizer, and it's also a dandy explosive. 1912, 1914, Karl Haber and Otto Weiss won the Nobel Prize for chemistry by developing the Haber-Weiss reaction, which was a reaction to take atmospheric nitrogen and synthetically produce organic nitrogen. You can't make fertilizer out of atmospheric nitrogen, N2. But if you have ammonia or urea, you can use that as a fertilizer. At the time, the Germans were actually mowing down to the sea level islands in the Pacific where seabirds had dropped centuries of guano because they could get that and isolate the urea for fertilizers in Germany. Now they could make their own. The downside of that, the double-edged sword, was that they also convinced themselves they could make explosives sufficient to sustain Germany in a world war. So without the Haber-Weiss reaction, there might not have been a World War I. I'm sure we would have figured it out by the 40s, but in any case, urea is the model reactions for polyurethane, and they're made today basically the same way they were then. You decide what you want and overall characteristics. Let's say we wanted a polyurethane that was going to be flexible. We're going to make floor poly, okay? Poly for floor, or a wipe-on poly. These are mostly aliphatic polyurethanes. We take that short little molecule with the two aromatic rings, and we put a big long carbon chain in there. And just looking at how it goes together, you're going to see there's more latitude to bend. So you put the property of the fin that you want for the finish in the molecule that makes up the finish. Very clever, those Germans. They do, on the whole, do good work. So the film finishes, if you're coming from a background in flat work, you're going to be using the same sort of film finishes: shellac, stains, dyes, which we're not going to talk about, the urethanes of the various different varieties. And now that you know there's a difference, next time you go look for a polyurethane, you're going to look at the label and you're going to see what's in it. That's the other thing I want you to understand. You need to know what's in stuff before you use it. And that's become a big point of contention about finishes on wood products. But the urethanes, the lacquers, shellacs, you've used these before in these finishes. The rules are not much different. If you like the way it worked on a mahogany bed that you made, it's going to work about the same way on a piece of turned mahogany. What's not so common in flat work is the use of an oil finish. Now, it used to be that we would have what was called a hand-rubbed oil finish on every piece of flat work. That was before there were synthetic finishes. When shellac was reserved for the King of France because it was too expensive for everybody else, the oil, and we used all kinds of oil back in the old days. My grandfather was a cabinet maker. He was the the cabinet maker for a little college in Northwest Missouri. And he goes back into the 20s. So this was kind of before the synthetic stains things. You know, he would use all kinds of oil. He actually, one of his favorite finishes was goose fat diluted with alcohol. You heat it up and you thin it out. And what you've got is basically an oil, as it turns out, a fairly highly polyunsaturated oil. And we'll get to why that's important in a minute. And he can rub that, and with the heat of the elbow grease, could compel that into the wood, and you wound up with a hand rubbed oil finish, which looked pretty good. I think it was kind of hard to get it uniform. So those sort of exotic finishes went away very quickly as better things came along. But the oil and the oil wax finish are sort of unique these days to wood turning. And that's because we very often make things that are for food use. And the oils are a little more food friendly. Let's talk about the drying oils. We've mentioned them a couple of times. The drying oil is this big term. And remember what I said about drying. We're not talking about water evaporating. We're talking about liquids becoming a solid. We're talking about state changes, liquid to solid. That's drying in the context of polymer chemistry. The natural drying oils was linseed, tung oil, walnut oil, poppy seed, perea oil, which is very rare and very tasty. It's a very common spice in Spanish food. You don't see enough of it to actually see it as a wood finishing product, but it's a drying oil. It falls into it. Now, I suspect you knew that polyunsaturated fatty acids were important and good for your heart. I suspect you did not know that they were also essential to your wood finishes. The drying oils are all polyunsaturated, and what that means we will see in a moment. All of these drying oils have a number of unsaturated bonds. What is a saturated bond? What's a saturated fat? What's an unsaturated fat? The saturated fat is a string of carbon with 2 hydrogens on it. As long as it's going to go, it's up to the end, which will have 3 hydrogens, and the very first one, which will have 2 oxygens on it. That's a saturated fat. It's saturated with hydrogen. Very high energy, burn very hot, will, turn solid at fairly warm temperatures. This is why they're important for your heart. The polyunsaturated, those carbon-carbon bonds are not saturated with hydrogen. They have a double bond in there. And it's those double bonds that allow the fatty acid molecules to bond to one another. So what we're talking about now is what's become known as organic plastics. The polyunsaturated fatty acids, the drying oils, used to be the essential element for oil-based paints. You got to paint, it was the solvent, the liquid was linseed oil or some other unsaturated oil. And that linseed oil bonded to itself. It reacted with itself and it became a solid. It dried. The oil paint dried because the oil went from a liquid to a solid state. Okay. Now we've replaced that linseed oil with molecules belonging to the alkyd family, which are sort of synthetic polyunsaturated fatty acid-ish sorts of molecules. But the chemistry of the linseed oil and the other drying oil has been used for a very long time to make any number of things. We try to delve into history when it's appropriate. The first plastic. In 1897, Adolf Hitler's cat was wandering around the lab and he tipped a bottle of formaldehyde over into his milk bowl. Well, they found the cat dead the next morning. But they also found that the bowl had become a solid, this white solid, what we now know as casein plastic. Milk was the source of the first plastics. And it's the same chemistry in that bowl with the formaldehyde that we're going to talk about with the drying oils. We try not to kill the cats, but that formaldehyde did a fine job. We still find the casein plastics. The first thing that was made out of the casein plastics were these knitting needles, because you could extrude that white material into very easily sized things. And these are still highly prized. Let's just pass them around. Those are still highly prized because they don't get cold. People who have arthritis or hand problems like the knitting needles because they don't get cold in their hands. They pick up the heat from the body and they stay warm. And they're also slightly flexible. That's solid milk that's been extruded into that shape. We also can find it at Craft Supply. If you look up alternative ivory, that's casein plastic. And it looks and turns just like ivory. It's the same stuff that the cat made in the bowl that day in 1897. Not quite as crude, but basically the same stuff. And the no, casein is the protein, the most common protein in milk. And no, it doesn't say what the cat's name is. That seems unfair, doesn't it? This animal gives up its life to open, a brand new multi-million-dollar, billion-dollar industry, and he doesn't get the name credit. Yeah. Now, casein is the milk protein that is tacked together by the formaldehyde to make the casein plastic. Have you ever, just to have to turn something different, it actually turns in a very interesting way. I have turned ivory, and this feels very much like real ivory. So it's kind of fun to work with. So the drying oils that we talked about, linseed oil, tongue oil, walnut oil, poppy seed oil, these have been around forever. We've known about them for a very long time, particularly linseed oil. Linseed oil goes back hundreds of years. Linseed oil is what the British painted the masts of their sailing ships with, because it in the sun would harden, protect the wood of the mast, and it turned a very military black color. In our context, linseed oil is a problem as a finish because it turns black. But we've been using linseed oil for all sorts of things. Linseed oil, if we see that the molecular structure there is the major oil in linseed oil. And I see Steve looking at the parts of that, and some of them look familiar. There's linoleic acid, and the green part, and linolenic acid, the red part. Those are the two fatty acids that we have to have in our diet. Those are the essential fats that fatty acids we have to get from our diet because we can't make them. And if you'll notice the unsaturations, the place where there's two lines between carbons, the double bond, those are polyunsaturated fatty acids. And then the third one is oleic acid, which is the unsaturated fatty acid in olive oil. It's a non-unsaturation. We can make it, but we've always gotten it from linseed oil. Linseed oil has been used for a variety of things before we understood anything about it. The picture there, you see the flax plant where the flax fiber for linen is isolated. And from that, we get the seeds. And from the seeds, we press the oil. That's linseed oil. Now, if you took that and you blew hot air through it, just literally blew hot air through it, so you had hot air bubbles going through it, you'd wind up with something that's called boiled linseed oil. Boiled linseed oil is not actually boiled. It's just heated. And as we're going to see in just a minute, that causes a change of state. The last little sort of thing, the brown crackers over here, if you blow enough hot air through linseed oil, that's what you get. That's the linseed paste or linseed residue. That has been manufactured as a cattle food for literally centuries. So we had no idea what we were doing, but we've been doing this for a very long time. That is one of the most nutrient-rich materials in the animal husbandry diet because it supplies two essential fatty acids. Cattle don't make linolenic or linoleic acid either, but we sure are glad they put it in our milk, that they produce it, they release it into the milk. So they need that as well as the protein, because the linseed oil is fairly high in protein also. So how does all this work? Remember I talked about the unsaturated fatty acids, the double lines? Without going too deep into the chemistry of it, chemistry works about imbalance in reactivity. You have places that are highly reactive and places that are highly reactive maybe for another reason. A double bond is an electron-rich area, and at the end of that electron-rich area is an electron-poor area. Things like oxygen molecules are always looking for electrons. So if we take our polyunsaturated fatty acid out there in the presence of oxygen, some heat, some light, we wind up with the peroxy intermediate. This is intrinsically unstable, as well as those two double bonds that close together. So that collapses and it bonds to a double bond on another molecule, and voila, we have a cross-linked polyunsaturated fatty acid. That's the drying oil. That's whether they're synthetic drying oils or natural drying oils, that's how they go from liquid to solid. They bond to each other. There's no liquid lost. It's not evaporative. It's a reactive condensation. And the next one, we have another oxygen molecule or water. We lose the water, and the process repeats itself over and over again. Pretty soon you have this net of fibers bonding to each other, and you wind up converting your liquid to a solid. If you're using walnut oil and your fiber and your friction polishing, that's what you're making in the surface of the wood. You're making that cross strand conjugate that becomes a solid. If you've ever dropped a little walnut oil on the bench and you come back and it's kind of this gooey plastic stuff, you're on the way to becoming a solid block of walnut oil. So the linseed oil and the tung oil and the walnut oil and the poppy seed oil have the same polyunsaturated fatty acids of different mixtures, but they're large quantities of polyunsaturated fatty acids, and they will all react with themselves to self-dry, to reactively condense. What's the difference between them? Why did we start out using linseed oil? We've been making walnut oil for the kitchen for years. Well, the difference between them is the rate at which this condensation takes place. Linseed oil self-polymerizes very, very fast. So fast, in fact, it generates heat. It's exothermic. This is why in the old days, when you used a rag to wipe up the paint, you didn't throw that paint-soaked rag in the wastebasket, because you were going to have a fire. Linseed oil was a fire hazard because it's the reaction where it's bonding to itself goes so fast it releases heat and actually starts a fire. Tung oil is not quite as fast. It is also considered to be something of a fire hazard. Although I will admit I have tried to get tung oil rags to burn and I couldn't do it. Maybe we just had fire retardant rags, I don't know. Walnut oil is a little bit slower yet. Walnut oil, although technically, because it is a drying oil, it's considered to be a fire hazard. I have tried very hard to get a fire started with walnut oil, and I can't do it. You know, even when I put paper around the rags, no joy. So the difference between the drying oils has to do with the rate of polymerization. The faster it goes, the more heat's generated. Also, the faster it goes, the more coarse the final product is. So linseed oil will, in its final configuration, be a very rough, not fine textured solid, whereas walnut oil is a very fine, smooth, something you'd like to put on a piece of wood, maybe. and get a nice smooth finish across your beautifully finished and sanded surface. The other thing about linseed oil, linoleum. Well, the linen linoleum comes from linseed oil because that's what linoleum was made from. So you see, it's also why linoleum is actually a fire hazard. Even though it's in a polymerized state, it's still readily flammable. So the linseed oil, the walnut oil, the tung oil, they're all useful oils. Tung oil I like and I use every now and then. It's a good compromise. It's going to set up quicker than the walnut oil. It's not going to have as fine a texture, and it's going to turn yellow over time. Now on walnut, it actually kind of adds sort of an amber undertone to the dark wood. So it's really not that big a deal. And I have in fact been known to add small amounts of tung oil to the walnut oil I'm going to use as a finish. It doesn't function catalytically. I told this to someone who thought, well, it's a catalyst. I said, no, it's not catalytic because it's consumed in the process. A catalyst is not consumed in the overall process. I think what it does is that it warms it up a little bit. You get a little bit of heat released locally, which is the most efficient, standing on the fire like here is an easier way to get warm than standing under a cold sun. Well, the heat is closer. When you have the heat being generated within the finishing layer itself, it's going to speed things up a bit. So you didn't hear that from me, by the way. We would never sully our walnut oil with something so mundane as tung nut juice, unless we really needed to. Anyway, tung oil makes a very hard surface. That's the other thing about it. It's not as hard as linoleum, but it is a little more tactily dense than the finish that you get with the walnut oil. Now, you can buy lots of finishing oils that are not drying oils. They might say they are, but in fact they're not. And this has been kind of a problem, and where the notion of food sensitivity sort of comes into the finishing. Drying agents, the big class of molecular additives, can be used to harden oils that are not natural drying oils. In fact, you can take paraffin oil, mineral oil. You put enough uruchinol in it, and it will act like a drying oil. Of course, keep in mind, you're going to have to go out and harvest the uruchinol from the poison ivy that grows behind your house, but that will work. The drying agents simulate that electronic interaction between the chains. It makes artificial centers of reactivity and cross-links these oils that would not dry normally by the actions of the drying agents. Uruchinol has, if you touch an oil that has been treated with uruchinol, you will get the same symptoms that you do from exposure to poison ivy. Fortunately, I don't get poison ivy, but I don't use uruchinol either. There are lots of other common drying agents, and most of these are metal ions. And years and years of toxicological research, these things kind of raise my eyelids when I see cadmium and cobalt and arsenic and lead. I sort of worry. They artificially electronically distort the carbon backbones of these non-drying oils so that they become reactive, and you do get the cross-linking effects, making drying oils out of non-drying oils. Uruchinol is an aromatic, and it's not consumed in the process, and it will eventually evaporate or leach away from the site where it's used. The metal ions are not volatile. They stay where they're put, and they're not trapped within the hardened non-drying oil surface finish. So what you have then is a source of things that you really don't want around food. So if you have an oil, a bowl finished with a drying agent dried oil, You can wipe over the inside of that, or as it ages and the finish begins to break down, you will find these metallic drying agents. Now, these are accumulated. We don't pass them. We make pounds of a molecule in our liver that has a specific function of binding them and keeping them out of harm's way. Eventually, exposure could become a problem. I don't honestly think that these metal ions become a health hazard, but there's no basement threshold of the toxicity for any of these. There's no greater than 0.1 nanograms per kilogram for an LD50. There's no known bottom to the toxicity of these things. So the drying oils or the drying agents are something you just stay away from. Now, there are some aromatic drying agents, uruchinol I mentioned. There's some that are made from naphtha that will eventually evaporate away from the piece. Also, methyl ethyl ketone can be used as a drying agent. And it also is very volatile and eventually will gas away. So we've got all of these types of finishes. What the finish does, what the molecular level is the same for the oil and for the polyurethane. It all depends on the length of the backbone. Is it flexible? Is it brittle? Is it going to make a very hard finish? Is it going to make a more soft, more tractable finish? Are there bad finishes? Yeah, there are. Mineral oil, with the exception of using it as a sanding lubricant, has no place in the wood shop. Unless you're going to, dose it with the uruchinol or the arsenic or the lead to get it to set up in the wood, it's going to evaporate within 30 days. If you're interested, I will tell you how. Well, I guess everyone in the wood business ought to know this. The story about the butcher's block and the mineral oil, horse laxative, it was in those days, paraffin oil. Why does the butcher coat his block with mineral oil? And the people say, well, it's to finish it. No, it really does not do any good. It goes down into the wood. At the end of the day, a butcher has a big wooden block full of blood and meat and other tasty things. He's got a knife that looks a lot like the tool you scoop the seat of a chair out with, which has a name. Scorpion. Okay. And he takes that and he runs it across the top of the block, and he scrapes off all of the wood that's been softened enough to come off. Okay. He then covers that with mineral oil for no other reason than it keeps the liquid in the block from going somewhere else. It's not going to harden. It doesn't sterilize the top of the block. In the morning, he's going to come back and he's going to take the scorpion. He's going to take the mineral oil off. He's going to take some baking soda and he's going to clean the surface of the butcher block. And that mineral oil has done nothing for the wood. Hasn't preserved it. It hasn't prevented any damage to it. It's just kind of got in the way of stuff that could get trapped in the wood fibers. So when people put mineral oil, and most of the butcher block finishes are just mineral oil, puts mineral oil on that butcher block, and they forget about it for a year. So, well, I finished it with mineral oil. No, 30 days later, that mineral oil was gone. The grain of your butcher block is opened, and it's trapping things. And there's folks growing there that you just might not want to know about. Mineral oil can leave behind a residue that will support bacterial growth. It will support fungal growth. It's not something you want on your cabinets. Okay, so mineral oil is not a good wood finish because it evaporates. It doesn't finish the wood. It doesn't even block it for very long. The other thing that I don't recommend, that I get not in trouble for, but I get questions about, is beeswax. Beeswax, it smells good. You put it on the wood, it's soft, goes on really nice. The problem is if that beeswax is not at least 30% contaminating wax, it's going to develop little white particles that look like flour within about 2 months. Because the beeswax, when exposed to oxygen, breaks down. Beeswax is the only wax that's meant to be digested. The bees eat it up again. They don't resecrete it, but they break it down, and that goes to feed the bees. So beeswax When you think about waxes, we've got a whole thing on waxes here if anybody's interested. Waxes look sort of like a C, where there's a link between two big long fatty acid arms. And in the middle of those fatty acid arms is an oxygen. So there are in fact not esters, but ethers and intrinsically unstable. When you expose that to oxygen, that wax starts to break down and you get these particles. If the beeswax is mixed with about 30% of actually almost any other wax, but the beeswax that you buy is 30 or more percent beeswax with some other wax, that will stop the snow formation. That will stop the particles. Yes. It's a matter of getting the wax, it's going to be a percentage of waxes. If the beeswax is diluted with 30% of that same volume of beeswax, or same volume of wax of, some other variety, paraffin wax or something like that, then you would get that. But you got to reach that 30% threshold. So if you're mixing beeswax with one of mine, where it's got a very small percentage of carnauba wax, you're not going to overcome the beeswax. But the good news is about the only place you're going to get pure beeswax is from a beekeeping store. The people that sell beeswax as a wood finish know this too. They read the literature, and they've mixed it with other things to prevent this dust formation. But still, it doesn't last very long. It is soft. It does break down even if it doesn't form the dust. It just does not serve the purpose of a good barrier. Oh, so the major difference between flat work and the lathe is, yes. Pardon? Okay, what about it? Something that's not mineral oil. A drying oil with a wax top coat. Pardon? Carnauba. It's going to spot a little bit, but just the drying oil or a polyurethane finish. If we're talking about kitchen cabinets. Now, if we're still talking about a butcher block in a butcher store, the mineral oil is fine because that process has worked for hundreds of years. But if we're talking about butcher block in a cabinet, you want something a little more durable. Shellac, it'll be fine, whatever. Yeah. The cutting board waxes are, the cutting board finishes are mostly mineral oil with some wax in it. And the wax, if you put that on and you heat it enough that it thins and runs into the wood, then you're fine. But you're better off using a drying oil or another oil of some sort to do that. Leaving it rough, yeah. And just clean it off every now and then. Now, the source of the energy to drive these processes is a major difference between flat work and turning. On flat work, you've got, the small little handhelds or, the elbow grease. We rely on the lathe to supply energy. And when I talk about friction polishing, what I'm talking about is the lathe turning the wood. There's friction polish, the noun, and friction polish, the verb. Walnut oil is a friction polish, the noun. It is something that we are going to polish with friction to make a finish. Friction polishing is the action of making that finish. The lathe lets us use French polish in a much more convenient fashion than the flat workers. We can actually use the energy of the lathe to polish the French polish, the high build friction polish as it's known in our neighborhood, and get that beneficial finish. But when I'm talking about friction polish,
put that food safe finish onto it. Set it at a moderate speed, somewhere around 1,000 RPM, and with the other finishes, you can apply directly to the towel. Cover the piece with a thin layer of the material. Now, this is the finish with the micro aggregated carnauba wax, the patented process that I had to develop to get wax to behave as though it's a liquid without the organic solvents to dissolve it. Okay, so we've got the surface pretty well saturated. We can turn up the lathe and polish that to a nice high satin finish. The look I was going for was not gloss, but in fact satin, in keeping with that wood should look like wood principle of the company. But if your surface is properly prepared, that's all it takes. And you see we now have a protected oil wax finish on this nice little walnut bowl.
Finishing is like choosing wine. What do you like? That's what I like. So I think let's see. The degree of shine, I will finish up on that. If you notice that bowl had a nice reflection. If you put on a finish and it's shiny when you're working on it and the shine goes away, well, I'm sorry about that. What's happened is the wood drew the finish down into it and it changed the aggregate reflection. Okay. What happened was, excuse me. The wood was not sealed sufficiently and the finish you put on was not stable. So as the structure of the finish changed, the light reflection changed and you wound up with a dull spot. How do you stop that? Sand, one more layer than you think you need, one more grit. Use a sanding sealer. Diluted shellac works just fine for a sanding sealer. Shellac sticks to everything and everything sticks to shellac. And get that surface actually uniform so that the finish you put on is not going to change in its density as time goes along. You got to shine there, it'll stay shiny as you go along. No, sanding sealer is the last thing you do. Okay, sanding sealer is the first wave of finishes. The sanding sealer seals after sanding. Now, there are some sanding sealers like nitrocellulose sanding sealer that say you can sand that once you put it on. And it's not that different from what I would call a sanding lubricant. The advantage of the sanding sealer, if you ever get a spot that's not cutting well, or you're sanding and you're not getting removal of the rough spot you think, you get out your can of spray shellac and you spot that with shellac. What that does is stiffen the fibers so that you get a little better cut or a little better cut with the sandpaper, because sandpaper is a cutting tool. The sanding sealer is doing the same thing. It can stiffen the fibers on the surface of the wood so that your sanding occurs a little better. But no, a sanding sealer, as I think of it, is the last thing you do before you start to put on your film finish. Let's see what we got here. I think we're about done. Sure. Yeah. It's going to go right in. It's going to set up again.
My name is Mike Meredith. I'm the doctor of Doctor's Woodshop. The governing principle of the Doctor's Woodshop finishes has always been wood. That is, the wood should feel like wood. Not some piece of plastic, not a thick bar top sort of
Well,
finish.
if I didn't like it, I wouldn't say it.
When I started making,
There we go. That's a movie about using Pens Plus on finishing a pepper mill. And you see the sanding sealer goes on. There was a question back. Yeah. Oh, no, there is plenty of reason. The oil is going to penetrate the wood. And that one coat is very likely not going to saturate the surface. So there's no reason to put 5 or 6 coats on, but 2 or 3 coats are going to fill up that, remember the Himalayas? We're filling up the canyons. And that second and third coat are going to fill the canyons a little better and give us a smoother surface to reflect the light. So it's yes. Oh, But what are, I'm sorry, say again? Yes. Well, yeah, yes. Well, that will give you as much as you've put on is the multiple layers. The interesting thing, I did an electron micrographic study of wood finishes. You know, I'm retired and I don't miss the students, but I do miss the toys in my lab. I had a scanning electron microscope, and I actually looked at some of the finished wood pieces. And what you see are, if you put on one layer of stuff and, you know, of it, and put the second layer on, and I expected to see a second layer of finish, like you would see growth rings in a tree. No, the second layer is absorbed into the first. So as you keep adding stuff, every time you polish it, if you add more oil, you're gonna add to that that's in the finished layer already. You could. If I'm using just an oil wax finish, I expected the oil and the wax to stay separate, and they do, but I expected 2 layers of oil, 2 layers of wax. What I got was a big layer of oil and a big layer of wax. The buffing, the friction polishing, the polishing motion that's actually generating the heat. That's what sets the oil. I get calls from people and they say, well, the oil is not setting up. And I say, well, where do you live? And if they say Arizona, I tell them, go set it on the back porch for a couple of days, because that heat will set the oil. They just didn't buff it long enough. They didn't friction polish long enough to get it to set. Now with the Pens Plus, where you've got shellac and oil and wax, that's the one that really surprised me. I really expected that to segregate into shellac, oil and shellac and wax. The rule of thumb is like dissolves like. Shellac and oil are miscible, but not bed partners, as it were. What I saw was one thick layer of things that were not wax, and then a layer of wax on top. I put on a second coat of Pens Plus. I saw a thicker layer of shellac and oil, and a thicker layer of wax on top of that. So that explains something to me that I did not quite understand. With Pens Plus, if you put on too many coats, suddenly it starts to get cloudy. What's happening is you're not getting it hot enough to dissolve all of the pre-deposited Pens Plus and mix it with the fresh. So you've got two different phases of the finish that have not combined yet. So you just keep that rag on there, and eventually it'll get hot enough. Everything will melt back together and it'll be shiny again.
What is hot?
Huh?
What is
Hot is burning your fingers through the towel. That is my definition of hot. If you need to go get a glove, you're getting it hot enough. It is hot.
Can you repeat the question?
Can you get it too hot?
Thanks.
And the answer is yes, but you really have to work at it. And what you'll see is that it will just start, with Pens Plus, the shellac will just start breaking off. So sort of the reaction you would expect if you overheated the tabletop. There's one more thing I want to talk about here. Come on, get back there. We got about 15. Don't need that much. Yes, that is pure shellac that will be waxed. I'll repeat the question. If you go to Woodcraft or somewhere and buy shellac flakes, is that pure shellac? Yes. And it will be of different colors because shellac comes in different colors. It will be waxed or or not waxed. Natural shellac has about 5% wax by weight in it. And sometimes in processing, they remove the wax. The shellac that you buy that's clear coat, that's actually a sanding sealer and that has been de-waxed. What I'm looking for is that picture we had of, no. Well, there's Roger's questions. It was the description of Danish oil. And let's see. Anyway.
If we don't have a lot of time, if you could just go over some of the questions I had that talked about application.
Application, what I want to warn you about is Danish oil, about Watco in general. Among the chemical offenders, they are about the worst. But I can hear it just fine. Danish oil is supposed to be a varnish with a polymer of some sort and an oil. Okay. It's supposed to be a natural drying oil. Danish oil you get from Watco, if you look at the materials in it, there is nothing that suggests that there's any sort of natural drying oil in it. It's mineral spirits, and the big problem with it is Stoddard solvent. That's a distillation fraction that is made up of 4, 5, 6, 7 carbon hydrocarbons. They're all liver carcinogens. They all penetrate the skin. This is just not something you want in your shop. Anyway, let's get to Roger's questions. I think we've answered most of them. Oh, there was one. I have been known not to be very fond of cyanoacrylate as a finish. And the reason is that I don't particularly dislike it. It dislikes me. I have a genetic deficiency in an enzyme called diamine oxidase, which makes me sensitive to nitrites and sulfites, as well as acetic acid and histamine. There's some red wines I can't drink because of the histamine in it, because I don't have the enzyme required to get rid of it. A belt of cyanoacrylate in the nose is pure acetic acid. It's like 84% acetic acid. I get a vasodilation event in my face, blood pressure goes down I go. So I avoid cyanoacrylate. It's an okay finish. It looks like plastic. It feels like plastic. I don't care for it. And it's not as easy as a lot of people think it is. A lot of the questions had to do with my products. You know, what's the difference between Pens Plus and the high build friction polish? The difference is the wax. High build friction polish is for that hollow form that's going to look beautiful. Pens Plus is for the pen or the pizza cutter handle, the pepper mill, something that's going to be handled a little more, as a little more abuse. Anyway, the applications, all of my finishes are friction polishes, and they all go on in pretty much the same way. The way you saw in that bowl being finished, put them on a towel onto the surface. When they've been spread evenly, polished till you get the heat, and then let it set up that way. There is, repeat the question. Is there any advantage to polishing in the reverse direction? Not polishing, but sanding, yes. Sanding in the reverse direction As you sand, you can raise grain up. And if you sand in the opposite direction, you can take those after the fact raised grains down. Polishing, I don't think makes any difference. That's a guess. You're at the edge of my knowledge on that one. I think that's about all the time we're going to take for this.
Any questions from the Zoom crowd?
Thank you for hanging on, Zoomers. Finishing is as I said, this is an impossible topic because there are questions that you can't anticipate because there are situations that you can't anticipate. This wood, that finish, you want this look. What do you do? Do the experiment and find out for yourself, I think. Is the way to go about that. So with that, we'll say thank you. We'll see you next month where we're going to talk about the hybrid, turning the hybrid blanks.
One of the popular new finishes, the Rubio Monaco for flatwork.
I have not experimented. But if you know what it is, if it's a polyurethane-like material, so it's an epoxy. And it's going to be a non-penetrating finish. It depends if that's what you want, if you like the look, and if that's what you want. He's asking about Rubio, which is a two-part finish that's very common in flat work now. And I haven't played with it in the turning world, but it's going to be like an epoxy. And it's a non-penetrating finish. So is it going to sit on a flat surface well, or a curved surface? I don't know. Do the experiment.
Mike, what are your thoughts about wipe on poly?
Wipe on poly is a polyurethane that is made to be flexible, and it goes on very well. It's durable. It will stand up. It's a good finish if you like polyurethane. But stay away from the Watco poly. Just
The reason I say that, you shake the can with Watco polyurethane, it solidifies the can before you're. $30 later, I learned that. It specifically says don't shake it.
Yep. And now you know why, because you've introduced energy into an environment where you have reactive molecules. What they're going to do when you take them out and brush them and expose them to oxygen, they're going to solidify. That shaking will do the same thing. Yeah. Finishing is about what you like. Polyurethane is not what I like. So anyway, we'll call it quits. We got raffle tickets to buy, I'm sure. And we'll see you next month.
And we also didn't award the gift certificate to the show and tell. And I'll make a command decision. I'll go for the very thin, incredibly thin
The trembler sticks. God.
work here. So I forget who did that. Congratulations, thanks. Okay, guys, raffle time. As always, we appreciate if you could stack up the chairs after the raffle.